What up, Julia?
Hello.
All right, so do you have any updates or anything you want to talk about? Updates on the test or anything?
So my test is on Friday, I believe.
For sure, this is the third time, I think.
Yeah. So if we could just go over like Newton's laws and universal gravitation.
Okay, yeah, good to know. So the projectile motion won't be on it.
No.
Okay, that's good. Good for you. Okay, here we go. There's that. Share, hopefully. Can you see? Are you able to see that? Hey there. Can you hear me? Maybe I'm muted. Let me see. Can you hear me?
Yeah.
Okay, must be a little lag or something. Okay, great. So let me just do what we did before, so I don't tell you stuff you don't need. That was last time. Beginning. So you said you want Newton's law and universal gravitation.
Yes.
Okay, great. So we can kind of start from the beginning, and if it's not useful, then just speed me along, or if you want me to focus on something, just let me know. So this is the equation. You should hopefully know this well by now, right? We have big G, which is a number, and it depends on two masses. Sometimes it's not called M1 and M2. So remember, sometimes it's M and ME if you're dealing with Earth, right? Or something else. Point is, I don't care. I don't care what you call your variables. It's still the same equation. It doesn't change. I just called it something else, even though that seems kind of weird. It really is the same. D squared and, like the same thing, R plus H. It is the same equation. And I'll show you because I talked about this a little bit. Say I have two planets. This is really where it's useful to understand this. Okay, M1, like we do, M2. And let's even put this back to D squared. And the reason, okay, so we have our masses here, and we have almost everything we need. And we say, what's the force between these two things? Well, we need a little bit of information, and we say, well, D. Okay, there's D, and that's not true. It's always to the center of the object. And so when you're thinking about this equation, it's always wherever the center is. That's D, this big distance there, not anything else. And the force itself is always directed along that line. So the force on this guy, because of this one, is pointing towards it, right? And the same thing here, the force on this one, due to this guy, is pointing directly towards it, okay? And of course, because of Newton's third law, it is the same force. That's why we don't calculate two forces when we do this. They're the same. Now, hopefully we can give you some insight here on why. Let's do this on one page because this is your basic situation. But then you start looking at a planet and a person, or a planet, Earth, let's say, and then a person in orbit. And they're here because the orbit is some distance h, right? And it's the same all along the circle. That's not that important. But then you have the radius of the Earth. And you know that very well. And you might call it R sub E or just R. But just so you know, remember, variables don't matter. But we use RE to say, oh, that's the radius of the Earth. That's right. But you could just call it R, whatever you want. But then that's why this equation is the same down here. Now it's not D, even though I'm telling you over and over, trying to drill in your head, I don't care what we call it. The variables don't matter. It's still something squared. What is that something? The distance between the objects. So you can say this, but it's still d. And we talked about this a little bit before, because that distance, well, it's from the center of the planet. We know that, and then to the object. So you can call it d, but that's why these equations are the same. And so you'll probably see, a regular one, maybe not planets. You had been doing people even, and you don't really care about the radius of the person, right? It's just all there. But then you do the astronauts and the orbit one. So do you want to cover one of those examples that kind of focuses on this form of the equation?
Yes, please.
Okay. So I won't spend too much time trying to formulate this, but I can pull one from the thing if you want, but I could pull a problem from your notes, but I'm a strong believer that you got to do new problems and new things, because if you've already seen it, it's good practice. So if you're okay with that, astronaut in orbit.
Yeah.
Okay. At height of, he's pretty low, she's pretty low, 200 kilometers, and height of above Earth. Let's see, we know the mass of the Earth, we know the radius of the Earth, we're giving it h right now. So my numbers will be weird here, but because I'm making this up, how much do they weigh? So why don't you take a minute, or yeah, you can tell me what to write down, and try to solve this one. How much mass do they have? So whatever you want to do, if you want to do it on your paper, or just tell me what to write down.
Okay, so it would be the FG equals G M1 M2 over D squared equation.
Sure. So I do want to point out one thing. I know I've been telling you that it doesn't matter about D and R plus H, but this guy might want you to say, well, if he's telling you about these equations, it would actually be R plus H here. Just for the equation and your own understanding, maybe. And because they're a height above the Earth, that's why. Okay, so keep going. Go ahead. We'll write that down since.
So for the height, it would be 200 kilometers.
Great.
For FG, it would be 20 newtons.
Yep, definitely. What else?
G would be 6.67 times 10 to the negative 11. And then the radius, that's the one where it's like 9.7 something.
Yeah, it would be, well, it's the radius of the Earth, right?
Mm-hmm.
Okay, good. So yeah, whatever, you're right, whatever the numbers. I think it's 6.3. You want to use that one? If you don't have your sheet, I can also look it up. The number, it's not as important because you'll have that on your thing, right? Yeah, I'll double check, but yeah, that's good. What else do we need or have?
And then you're trying to find the math.
Which one? I guess it doesn't matter, right? Kind of a trick question.
Mhm.
So let's say it M1 because it doesn't matter. Anything else?
There's M2, but I'm not sure what it is.
So you're not sure of the number or what it represents, or both?
Oh, the number.
Okay, but you know it's the mass of the Earth, right?
Uh-huh.
Okay, cool. I think it's that one you were saying 9. I don't know. We'll just, I got it right here, so I'll look it up. Okay, so what is the next thing that you do to finish this off?
Then since you're finding mass 1, then you have to isolate M1.
Okay, how do I do that?
Um, oh gosh, I don't remember.
That's all right. So you want to use your algebra to get it by itself, right? So it involves canceling
Mhm.
stuff. And so the first thing I would do, well, normally I would multiply by this right first, but maybe you don't. So let's do that first. Multiply both sides by that, right?
Mhm.
And so what am I left with? Those cancel, right? So if I was to write a new equation, or if you can keep solving it, tell me what to write down.
Okay, so then you're left with r plus h squared times fg
Good.
equals g m1 m2.
Great. So what do I do now?
And then you divide by g m2.
Perfect. Because these cancel. And then obviously this is by itself when you could do it with both sides, like you said.
Mhm.
Great. So yeah, that's exactly right. And then what's the last step? Plug in the values, right? So almost, we have to make sure that our units are in the right thing, right? So you might want to say, what would you put here for R? Or let's make it easier, 200,
Mhm.
but wrong, right? This has to be in meters. So it'll be
Oh, okay.
times 10 to the third is kilometers, right? So now 200,000 meters. So yeah, that's kind of a weird thing because you're not going to be that far, but it doesn't matter. You still have to convert. And the same with this one here. You want to make sure it's in meters. Okay.
Mhm.
Because this value of G here, if you look at the units, you'll see that it's, I know we, G constant. Yeah, newtons times meters squared. That's what this thing is, the units of this thing. And it's important and kind of crazy and useless sometimes, but then you realize, oh no, if I'm using meters squared here, like that thing I'm using in meters, well, it can't be kilometers up here. You don't, it doesn't, you won't, it doesn't work out, the math, right?
Mhm.
So then all that's left is to do the calculation. Do you want to do it together or do you want to move on? Because for me, it's solved, but you know, you're going to have to do this on the test, of course. And you said you're okay. You'd gotten a little better at the calculator. But we can do whatever you want.
Um, can we go over it?
Yes, definitely. So do you want, okay, so you want me to go over it, each step? So what you would do here is, I mean, to make it easier, your life easier, rather than leaving it like this, right? It's technically done kind of, and whatever with those, but plug in your numbers and write it down so you make sure. So this is what I would do, right? Take one more step, takes a little bit more time. FG was 20, right? You want to write in all your values so you make sure that you do everything correctly. It's just about making less errors, right?
Mhm.
So then we got 10 to the 24th kg, and kg is, okay, good. Should be okay. And then we got our square up there. Okay, great. So then the first thing I would do, right, is take care of the parentheses in the square, kind of PEMDASes, even when you're just doing calculator stuff. It's useful. So 63,78,000 plus 200,000. Great. Get some number. 65,78,000. Square it. Let me know if I'm going too fast, or you want me to write something down. But I have 4.33 times 10 to the 13th. That's just taking care of that part there. And then I'll multiply by 20, just adding a factor of 2 and a 0. And then we'll divide by this guy, the big G, divided by 6.67, E minus 11. You get 1.297, 10 to the 25th, and then divide again by that. So just immediately press your divide button, 5.97 E 24, and a weird number because I didn't work it out in the beginning. So she only weighs 2 kilograms. Great. 2 apples is how much this person weighs. So did you get that number also?
Yes.
Okay, great. That's a good sign. So yeah, there's that one. That's kind of not really a standard one, but it's because we're solving for M, right? Not the easiest one you could get. The easiest one would not be doing any manipulations and you just plug it into a calculator. But I wouldn't be surprised if you saw this type of problem. There was also another one. As I'm looking for this, tell me if you want me to do another one like that. There was one where they give you the force of the person in newtons, like the weight on Earth, I think. It's kind of a little different one. And then it might have been the second to last lesson. Oh, there it is. I guess it's in the beginning. Yeah, this one here. This is a decent one. So, okay, 50 kg Astro. I think this will be useful to you. And since you only mentioned Newton's laws and this gravitation, I figure we could spend our time here. Of course, if you want to do something else, just let me know. So they weigh something, let's say 1100 at sea level. Okay, so here we got this. So this is the one where it's definitely a gravitation, universal law of gravitation problem, but it's a little different, right? But please always do the same thing. So what's the first step to solve this?
Make your list of everything.
Yeah, you got it. So tell me what to write down. If it's hard to read,
so mass 1 is 2.94 times 10 to the 26 kg.
Sorry. I don't know what's going on. It was you're all garbled because of slow connection, maybe. Sorry about that. Can you say it again?
M1 is 2.94 times 10 to the 26 kg.
Okay, great. What else?
Um, is the second mass 50 kilograms?
Yes. And the key here is kind of reading this, but those units always give it away because they're always going to give you those units.
Mm-hmm.
So good. Yes.
Um, G is 6.67 times 10 to the negative 11th. And then FG is 1100 newtons.
So got to be careful. This is the where it's hard, and or it's an extra step. It's actually not. I think is that. Yes, yes, of course. So, and the I'll write this last part down. That and then FG, and if you get that, it's not quite. And the reason is because they're standing on the planet, and that's the weight. And so we actually need to find gravitational acceleration. I'm looking at your notes here, and no, this isn't the one I thought it was. I thought this was because I picked this one because it was a different one. But yeah, and then you did use the weight here. It doesn't matter. Okay, so yeah, you are correct here. Sorry about that. I was trying to do one where you had to solve for this one and then put it back into the equation, but this was not the correct one. So sorry about that. And you are right, 1100 newtons, that's fine. And we have to find R, right?
Mm-hmm.
Okay, or D, I guess you want to call it. I wrote down radius, but it is D. Yeah, okay, this is right. And this is just a standard, again, gravitational law problem. So you could do it here. And so how would you go about solving? Which one do we solve for? And then how do we get it by itself?
Okay, so it's FG equals GM1 M2 over D squared. So we're solving for D, so you multiply D squared to both sides, and you get D squared times FG equals GM1 M2,
Yeah,
and then
then what do you do?
you divide by FG,
Mm-hmm.
and then you get D squared equals GM1 M2 over FG, and then you square root both sides.
Definitely, yes. And whenever you're solving for that distance, this is what you did. It's always the same. Hopefully you've seen that by now. And then we plug in the numbers, and if you want to go ahead, we can compare. Four. Is that what you got?
I'm still typing it in 1 second.
Sorry.
Yes.
Good. What are the units?
Um,
If you have trouble, you ask yourself, you go back to your problem and say, what did they want you to find?
the radius. So meters.
You got it. Radius is always a length. So yeah, meters. Good. Okay. That was the one that I wanted to do before. Okay. We can come back to that and I can give a break and we'll talk about Newton's laws here. What would you say? Let me go through notes. Let's make sure we get exactly what you need for Newton's laws. Oh, yeah. So if we got these two hockey players, just a baby, a big beefy guy, and it's hockey, so they run into each other, right? What is the force that if this guy exerts a force, right, F1, what direction is the force that this person exerts on that one? And is it the same, greater, less?
Oh wait, are you talking about the force of like the little person on the big person, or the big person on the little person?
So I'm saying that the force of the little person on the big person is this here, right?
Mm-hmm.
Hits them and it's just some value F1. We can call it 10 newtons, 50 newtons. I don't care. It doesn't matter. It's just some force. So yeah, but and then I'm asking, how big is the force? Is it compared to this one of the big guy on the little one?
Um, I want to say it's equal, but because the big person has like a bigger mass, it's kind of throwing me off.
Mm-hmm. Yeah, this guy definitely has a bigger mass, but this is the key here, Newton's third law. When two objects are touching each other and there's contact, it's always equal and opposite if a force is exerted. And we just said this little guy is exerting a force. They're in contact and there's some force hitting this big guy. But Newton's third law says that the same exact force comes back and hits the little guy in the opposite direction, right?
Mm-hmm.
That's Newton's third law. And then when you start talking about the masses, then you get a little bit of a deeper understanding. And so let's talk about that. So what do you, I mean, you'll see this later on if you get into energy and momentum for this class, where this is like the initial kind of situation. And then if I draw a final situation, right? And this little guy, I think he's in a heap over here, right? He's
Mm-hmm.
on the ground and broken. But this guy doesn't move at all. Like he was unaffected. He didn't even notice. He thought there was a bug in the room or something. And the point is he's still in his same spot there. And so how can we explain that? Or you tell me how you can explain that. If they experience the same force, right? How's this possible?
Um, I'm not really sure.
Well, you started to talk about it. You said, well, the masses are different. And that's the key insight here,
Oh, okay.
right? This guy has such a M1 is the mass of this guy, and it's so much smaller than M2,
Mm-hmm.
right? And so if it's the same force, well, Newton's second law, that's when we think about that. And that's when it brings it all together, kind of. Second law. What is Newton's second law? You tell me.
That's the one about like speed and velocity.
Not quite. Force? F net, maybe?
Yeah.
Yeah. So what is this equal to? The net force in general.
It's equal to the acceleration.
Yeah, almost. And there's also a constant out there. It's ma. So F equals ma. That's a key one you want to try to remember. Force, the total force, net, equals mass times acceleration.
Okay.
And if we understand this equation, then we can say here, oh, the forces were the same. So let's be real careful here. We've wrote this force F1 equals. So 1 just means this guy here, right? This is everything about him. And 2 is everything about this guy. And he's got a different equation, whatever his equation is. But it's this Newton's second law, but I've done 1 and 2 to denote them, right, for him. But we said that F1 is equal to F2, right?
Mm-hmm.
So this is getting maybe a little more mathy, but maybe it'll drive this home. This is Newton's third law. Remember, equal and opposite always. Newton's third, 3. But Newton's second in general is that F equals ma. And so if we take these two equations here, if we take that equation and those two equations there, then we're saying that M1A1 equals M2A2. And remember, this is the original situation. This guy, they hit each other, and this little one pushes back on the big guy, and they experience that force. But because of Newton's third law, the big guy exerts the same force. And since this guy weighs so much, Newton's second law tells us, well, if M is really, really large for some given force, there's not going to be much acceleration. And that's that idea of mass is kind of resistance to motion, inertia. You guys talked about that a little bit, I think. But that's why it's so hard to push a house. A person can't push a house. Why? Because the house weighs a lot, and a person cannot exert that force. So there's no acceleration, no change in motion. That's what it's saying here. And so that's kind of what happened here. This little guy just hit this giant house, and he got sent way back because now imagine, okay, the final point here is, say you push on a house and you give it 10 newtons, some number, I don't care. You just push it on a house. Now take that same exact force and put it onto a ball. Well, the ball goes flying, right? Does that make sense?
It kind of cut out a little bit.
Oh, sorry. Has that been happening a lot here?
Not really, just
okay.
That last analogy.
So yeah, you're pushing on a house and it's not moving, whatever, but I'm pushing on the house, giving it some force. That's what that means. And then say I give that same exact force to a ball or something small, like a calculator or a ball, but it's the same force. The house didn't move because it weighs so much, but that calculator, that ball only weighs a little bit, so it goes flying. And you can imagine that, I think, right? And this is why, because I'm exerting the same force, but because this ball has such a tiny mass, well, for the equation to be true, A has to be large. That's kind of the idea here. So that's kind of putting together Newton's third law and Newton's second law. Kind of taking what you're having your notes here, and at least what I've seen on tests before, there's never these questions that you're doing on your notes, which is unfortunate, but they always combine it into something you haven't seen. So hopefully that gives you
Yeah.
kind of a deeper understanding of it. And the idea is that the same force will accelerate a small mass a lot more than a large mass if you give it the same force.
Okay.
Okay, let's talk about this one. We spent a couple times on this, or a couple. This is just a kind of a smaller problem. How much does 5 pounds of bricks weigh? So my governing equation, do you know what it is? If I'm asking about weight.
Oh, weight, or W equals M times G.
Yes, beautiful. And so M times G, hey, this is a mass, right? And I know G, we know that by now is 9.8, right? You can write your units down or not. And so you say, oh, okay, 5 times 9.8. Done, right?
Mm-hmm.
So not quite, right? Because this is in pounds. And this guy is in, well, kilograms per meters squared. And so if you go back to your notes on Newton's first law, mass and weight, as well as the law of universal gravitation, that's what I was looking at, we have to convert this. And so that's why that's not quite correct. We have to say 5 pounds divided by 1. Here's our conversion factor that we spent a little time on, 1 kilogram. And remember, there's 2.2 pounds in a kilogram. So you have to write this down. Cross out your pounds. And then the true mass in kilograms is 5 divided by 2.2. That's the mass in kilograms. And then you can go into your thing and say 2.27 times 9.8. But let me write it down in the way that you have it on your notes and that we did it ourselves. So weight, of course, M times G. What is M? Well, again, it's 5 pounds. But I don't want pounds. I need kilograms. So that's why kilograms is in the numerator here. And to get rid of the pounds, how do I cross it out? Well, I have to divide by pounds. This is what we call the conversion factor. And so this guy here is M. And then we want to multiply again by G. And you have this here, and you can say that 1 kilogram to, of course, cross everything out, and you're left with newtons. But of course, this is just the same thing as doing it over here separately, right? And then just doing M times G, 2.27 times 9.8, you'll get the same answer in this case. So this thing weighs 22.2, and then newtons, always the units of weight.
Okay.
Yeah, that one's not too bad. But there is, and then of course, if you have, I mean, I'm looking at the universal gravitation one, determine the gravitational force between a 105-pound girl and the Earth while the girl stands at sea level. Well, your mass better be in kilograms, right? That's why. Oh, okay. Okay, so just one thing on this, because I told you, remember this, we had to convert that, and we said times it by 1,000 to go from kilometers to meters. So you don't have to do that if you take care of it in the denominator. And that's why we don't say, if we say this, and that's what you'd been doing in your notes. And I don't want to spend too much time. I just want to go back on that, because this is now taking care of that 1,000 in the numerator. So if you use this value of 6.378 for the radius of the Earth, right, then you can use just regular old kilometers in the numerator. But
okay.
Yeah, hopefully that's clear. It's always best to check, right, and make sure that you're doing that your numbers work out. But that's why sometimes 6.378, and you'll also see 66,378. That's only if you're in meters, right? For the other guys.
Mhm.
Okay, I was gonna do that one I want to do before. We got about 10 minutes, and because you said you want to do gravitation as well as Newton's first law, but I found that problem that I was trying to do earlier with the astronaut that was a little bit different, where you solve for FG first, or if you want to do something else, we can.
Um, we could do more like problems on Newton's laws that are like word problems rather than math problems.
So not math problems, more like qualitative problems.
Yeah.
So like, oh, okay. So just kind of maybe going over it myself or asking you about how to use it. I see what you're saying. Okay. Yeah, I'll just go through some examples here. We got, okay, so say a rifle is shooting a bullet. Great. Is the force that pushes the bullet forward equal to, greater than, or less than that force that the bullet exerts on the rifle? And if you want me to repeat it, that's fine. There's kind of said a lot.
I think it would be equal to.
Yeah, definitely right. Why? Newton's third law.
Mhm.
And just like those hockey players and other things that you think about, pushing on a house or whatever, the bullet doesn't weigh anything basically. And it obviously, a bullet goes really fast, even though it's the same force on the gun. But because the mass of the bullet is so small, that's why it accelerates, which does relate to velocity. High acceleration over time means high velocity, right? So,
Mhm.
and then the rifle, you have some kickback maybe, but it's not like it's flying backwards at 100 meters, it goes really fast, right? Because it has a lot of mass. Rifle is a lot bigger than a bullet. So that's why. What about, think about a bat and a baseball, right? Or better yet, a golf ball and a golf club. So what is the force on those two things? The force on the ball compared to the force on the club. Is it, which one of these would it be? The force on the ball compared to the force on the club, if they're in contact. And I'll draw it
Equal
very,
to.
it's equal to, yeah, so hopefully you're getting the point here. It's the same
Mhm.
every time. Yeah, and truly, if you think about that and remember that they have to be in contact, like remember the example you had about the coin in the water, but it
Mhm.
wasn't correct because the water was not the original force. It has to be like the coin on you or the coin on the water versus the water on the coin. There can't be, different things going on. It's only two objects that are in contact. And then of course
Okay.
Newton's second law, and thinking about, why does this bullet go so fast but the gun doesn't? And it's because of Newton's second law. And F equals ma. Larger mass means a smaller acceleration. And then I guess the one we didn't really talk about was Newton's first law. So yeah, if something is moving, it's kind of a special case really of Newton's second law. But if I have something going along here, right, some velocity v, well, for it to do something else, notice that means anything. For it to slow down or speed up, I better have some net force acting on it. That is non-zero. That's all that means. It's not equal to zero. So that includes turning, like if it's here and it's just moving through space, some constant velocity, important, right? And then I want it to go like that. Well, I'm changing the velocity, even if it has the same speed. I don't know if you guys got into that too much, but I have to do a force for it to turn. There has to be some force. Otherwise, if there's no force, it'll just keep going on forever, right?
Mhm.
And like I said, it really is a special case where of Newton's second law, where if F net is equal to 0, no change in velocity.
So if F net equals 0, there's no change?
Yeah, there can't be any change.
Okay.
Yeah, and the reason is because a change in velocity actually is the acceleration. And when you look at, I just wrote it a little differently, the F net, but I just solved for, in fact, let me keep that. If you have F net equals what? M times A, right? We'll divide both by M, and that's how you get this one here, right?
Mhm.
It's kind of a different way to think about Newton's second law. But this is Newton's first law. But if a change in velocity is acceleration, well, that's what Newton's second law tells us. That's why the first is just a special case of the second. Yeah. I didn't see any other, I didn't see anything else on Newton's first law. Oh yeah, there's this quiz. Okay, here we go. And so yeah, according to the first and second laws, an object or body with zero net force acting upon it will do one of two things. And you said stay or remain in motion. So remain in motion is what I was talking about here, right? It's just going and it's not going to do anything. It's not going to slow down. It's not going to speed up. The velocity doesn't change.
Mhm.
It has to be a net force for something to happen. Object, right? Yeah, that quiz is, I recommend you go over that quiz and just kind of maybe quiz yourself or have somebody else ask you the questions and try to think about that again and really understand the quiz on Newton's laws of motion. That's a good one because it's all qualitative and it's basically everything we've been talking about. I mean, this lesson about Newton's laws, you know, that 2-engine aircraft, it loses one of its engines. Well, what happens? Well, it can't accelerate as fast. The mass stays the same, right? So
Mhm.
if it's same mass and you lose an engine, you have less force. And so because of Newton's second law here, F equals ma. Well, if this goes in half, now it's F over 2, right? I lost an engine. So that means that if I have the same mass, this acceleration has to go in half for the equation to be true, right?
Mhm.
Kind of like if you do one thing to one side, you have to do it to the other. So I divided by 2 on one side. Well, I better do it on the other side somehow. So yeah, hopefully that's time right now, but hopefully that was helpful and you got something good out of this.
Yeah.
Okay, good. So yeah, let me know if you need anything else and see you later.
Okay. Thank you.
All right, thanks. Have a good night.
Bye.